Hello, everybody. Welcome to the last technical session of SVR Symposium Virtual Reality. We have here four amazing articles that we are going to present right now. Um, First of all, you are very welcome to make questions and try to make some more active conference. You can post your questions in the YouTube channel or in the Discord channel as well. Okay, we are expecting you to really make this more interesting for everybody. Okay. I think you should start with the first technical paper. Oh, it's there. Systematic review of virtual reality solutions employing artificial intelligence methods. Okay? There are 11 authors. Tainan Ribeiro Oliveira, Matheus Moura da Silva, Rafael Antônio Nepomuceno Spinacé, Gabriel Dissen Ludke, Matheus Ruiz Soares Gaudio, Guilherme Iglesias Rocha Gomes, Juan Guio Contini, Daniel Vargens, Marcelo Queiroz Smith, Rodrigo Varejão Andreão, Mário Mestria. We have three people for presenting this paper. It's Matheus Rui, Rafael Spinacé, and Guilherme Iglesias. Well, let's see first the movie, please.
Hello, this work presents a systematic review of a range of applications of the use of virtual reality integrated with artificial intelligence solutions. Our team is composed of 3 professors and 8 students. My name is Rafael, and I am in a technical course in electrical technology. During this presentation, there will also be 2 other students speaking, Guilherme, who is in a technical course in mechanics, and Matheus, an undergraduate student in electrical engineering. We study at Instituto Federal do Espírito Santo and have a partnership with the mining company Vale do Rio Doce. The motivation for this research was to study how both technologies of artificial intelligence and virtual reality can work with one another and how they can contribute to different fields. To select the literature to be reviewed, we use the search engine Google Scholar and the database of Elsevier Scopus, ACM Digital Library, and IEEE Explore Digital Library. We search only for applied papers that apply both for virtual reality and artificial intelligence, as research in the field has the objective to solve problems in the context of industries, commerce, and service. The information on the papers reviewed we collected in a questionnaire on the following points: authors, title, year, country, type, if it's applied or review, AI techniques, application fields, advantages, limitations, trends, and opportunities, as well as economic sector, if it's either manufacturing or logistics. The 11 authors of this paper were divided into 4 different groups to evaluate a set of papers, and to provide results, analysis, and discussions. Based on the objective of this review, the following research questions were raised. RQ1, which AI techniques are most applied with VR? RQ2, which fields employ AI in VR-based applications? RQ3, what are the advantages and limitations of using AI methods in VR-based applications? RQ4, how can AI contribute to new trends and opportunities for VR-based applications? RQ5, how can AI and VR aid intelligent manufacturing or logistics? As to obtain relevant results to answer these questions, the following inclusion and exclusion criteria were made. For exclusion, theses, monographs, books, technical documents and reports, and theoretical papers, duplicate publications, papers in languages other than English, and review papers. For inclusion criteria, applied papers, studies within a 5-year period, context of geographical region, AI fields.
Besides the research questions, it was also considered relevant information about the papers. Regarding the year, we can see a growth in studies of this area, mostly in 2020, where 44% of the papers are, indicating an increase in interest in this topic, being that most of them are produced in China. Analyzing the economic sector and the field of research, we can see that most of the papers are yet related to education, as we can see here and here. But also we can see an emerging second place here in health and here in manufacturing, indicating more practical applications for VR. Now, with the research questions, the first one we had was, which AI techniques are the most applied with virtual reality? In this work, we divided artificial intelligence techniques in 5 big groups. For virtual reality, neural network as a subfield of machine learning was the most used, and also it was used for image reconstruction and 3D environments. For augmented reality, we could determine that deep learning as a subfield of machine learning was the most used. In this case, use it to accomplish the real-time requirements of this technology. The second research question was, what fields employ artificial intelligence in VR-based applications? The results revealed some fields of real-world applications using machine learning to analyze images and videos, such as teleconference, human-robot interaction, behavior recognition, target recognition, hand-track system, and facial expression recognition. Also, we can see applications in rendering 3D models and 3D videos, which can bring enhanced visual perception and aesthetic, increasing sense of immersion and improving naturalness of virtual characters. AI was also applied to predict VR sickness before the occurrence, ensuring a safer and better experience to the user. The third question was, what are the advantages and limitations of using AI methods in VR-based applications? After the analysis, we could see the effective use of data as the main advantage, improving accuracy and efficiency. AI was also used to upgrade user experience, making it more realistic and intuitive. However, the computational costs increased, and some projects needed a big dataset, hampering scalability and adaptability. Also, we can highlight side effects such as nausea provoked from the exposure to VR devices.
4. How can AI contribute to new trends and opportunities for VR-based applications? To address the above question, we analyzed various papers. Different approaches are presented for human pose estimation and reenactment, one of the core elements of VR technology. All methods use novel AI integration techniques to achieve this goal. AI can contribute by object recognition and image processing to create more efficient and simple applications. The adoption of portable devices will open additional opportunities for the personalization of autonomous vehicles. AI also allows the design of smarter devices to complete chemical complex experiments. AI can be used for the efficiency analysis of smart investment products. Finally, AI can contribute to the applications of VR in health to promote efficiency and precision in surgical operations. How can AI and VR assist in intelligent manufacturing or logistics? The use of machine learning along with image data processing methods increase the degree of reliability in the analysis of human rehabilitation, decreasing the efforts of therapies. AI and VR can help with the quality control of materials and products, and ensure better use of materials. AI and VR can help to improve the level of safety in the work of road traffic. AI can minimize the energy consumption of all equipment, optimize the positions of the GVs and UAVs. Finally, AI can assist in the manufacturing process to improve the stages of industrial product development, making factories more efficient and smarter. Discussion and conclusion. The findings revealed several fields of applications that employ AI in VR, such as teleconferencing, behavior recognition, and health. We conclude that machine learning is the most applied AI scientific technique in VR applications. When using AI methods in VR applications, the main advantages are high precision of the algorithms and high efficiency. The main limitations are high computational costs and the dependence on the dataset. This review can identify new trends, advantages, and help with other intelligent systems such as education and business. The limitations of our work were the scope of keywords adopted and chosen. Those are some references. For a complete list, please see the article. Thank you very much.
Perfect, thank you. And really, I forgot to mention, you all are for the Instituto Federal do Espírito Santo. Good, good. Let me see. I was just paying attention. Let me see if there's some questions. No, just welcome. Let's see here. No. Okay. I think it's very interesting what you presented here. And I think everybody is something that you can perceive the increased amount of AI papers and works and whatever in this virtual reality field. It's really something we can notice. It's good because you show the numbers that are really amazing in the past few years how this increased. I'm curious. I don't know if did you see if it's okay? It's a trend, but it is replacing. Of course, it's replacing other areas. Do you like? I mean, computational visualization, we have some traditional ways of doing. Are you working? Have you worked on trying to evaluate what is it replacing? Which fields are replacing this AI in VR?
Uh, this work didn't evaluate this field exactly,
Okay.
but of course there are new places that come with this technology with AI. I've one thing that we could see that some trainings in business companies are being replaced with AI and virtual reality to uh, make the cost lower.
Okay, I think you kind of answer one of the questions, that is, what are the research opportunities you identified?
Uh, can you repeat, please?
Research opportunities. Is it appearing new opportunities? Oh, but that's the question. Opportunities for with this possibility.
Yeah, I got it.
Okay.
One of the things I said is true. Is true. We can make trainings in business cheaper with this technology. We can see also a trend in social media to improve the customer experience.
Okay. Uh,
Uh,
well,
so
Yeah, we see.
the our article can identify a lot of opportunities in very in very in some very important sectors, just like the sector of autonomous vehicles, in part of chemical experiments, in health, and in 3D recognition.
okay. You want to say something, Rafael? No.
Yeah, we're gonna say that similar to what you said, that a lot of fields have been integrating AI technology. For example, translation techniques have been trying to apply AI to make the translations more easy to make and more precise, even to the point where people are attempting to make automatic speak to speak translation techniques based on AI. So there's that.
Okay. How long have you been working this research?
We started in the beginning of last year. Last year, no, excuse, this year.
Okay. Then it's
We
about
started in March. In March,
March. It's about
March.
7 months more or less. Oh, but you submit the paper a long time
Uh,
ago. Okay. Then,
Yeah.
okay. It was a quick. No, it's very good. Very good. I was very impressed with China. When you mentioned that there is a lot of research from China, you mean from Chinese people or for the China country only?
a China country,
Okay.
not only for Chinese people, but made in China and paid by the Chinese people and by Chinese business.
Okay. Yeah, no, because actually, I believe there is even more because there is people from China. Let's see, they in
Yeah,
a lot in the many countries, and China is really impressive.
Yeah,
Impressive.
it's fairly interesting how China has been growing a lot in various fields, especially this research field of AI. There's that.
Yeah, it's really interesting. I agree. Let me see here. Okay. I have just one last point about AR. Appears that there is I didn't know this, but there's a more interesting in AR than VR. Did you manage that? Check this. More research being doing with augmented reality than virtual reality, with machine learning, of course, or artificial intelligence, of course. Did you understand my question? No.
Don't get
Okay.
it totally.
Okay. Are there more research being done in augmented reality than virtual reality with artificial intelligence? Did you?
Yeah, our work was focused on virtual reality. So the augmented reality that came to our work was by coincidence. We can say it, but the sensation it gives it's even half of both of them are equally uh, researched.
Okay. Oh, perfect. I don't know if there's someone else interested in making a question. I don't think. Well, then I would like to thank you again. Thank you a lot actually for the presentation and for the questions. Thank you.
Thanks for the opportunity.
Thank you.
Next paper: comparison of machine learning algorithms for automatic assessment of performance in a virtual reality dental simulator by Lucas Salaberry, Romero Tori, and Fatima Nunes, all from University of São Paulo. Okay, let's see the video.
Hello, my name is Lucas Laberry, and I'm going to present the paper Comparison of Machine Learning Algorithms for Automatic Assessment of Performance in a Virtual Reality Dental Simulator. The authors are myself, Romero Tori, and Fatima Nunes. So virtual reality simulator for training of medical procedures has seen a growth in popularity recently, and this is for the advantage that they have. For example, the risk-free training, because the patient is a virtual one. There is usually minimal material loss in those simulators, and the capability of collecting data such as the trajectory of the instrument and others. So the objectives of this study is to use the data collected in simulators to calculate performance metrics, which are metrics related to how well the participant has performed in the simulator, and use them as features to train machine learning algorithms and compare those algorithms for skill assessment. Use the Videodont simulator, which is a virtual reality dental simulator. Right now the focus is on the training of the inferior alveolar nerve block technique. It was developed in a partnership between Interlab Lapis and Lacici, and we use a haptic device for the first feedback during the procedure and a head-mounted display for the immersion of the participants. So in experiments, we collected data. For this study, we considered the data from 155 participants, from which 28% are novices. So there were undergraduate students of dentistry who did not know how to perform the inferior alveolar nerve block technique, and 72% were experts, which were students that already knew how to perform the procedure, or were postgraduate students, professors, and professional dentists, all of which knew how to do the procedure. So during the experiment, we explain how to do the procedure, and then they are asked to do it in the virtual patient. So here we have the trajectory that the syringe must do during the procedure. We divided this trajectory in 4 segments. Segment A is the whole trajectory before the syringe enters the patient mouth. B is the trajectory of the syringe inside the mouth until it hits the target. And C and D is the needle of the syringe entering and retracting from the soft tissue of the mouth. And we have a 5th segment, which is the combination of A, B, C, and D, so it's basically the entire trajectory. And for each of those segments, we calculated some features, for example, related to the velocity, to the acceleration, the time spent on each of the segments, and so on, to a total of 98 total features. To calibrate and to train the models, we use a stratified tenfold cross-validation. We had scaling for the classification for the algorithms that needed scaling. For balancing, we used the small atomic links because the data set was unbalanced. It had more experts than novices. From the original data set with 98 features, we also calculated two more data sets. One of them was using the ReliefF feature selection algorithm, and the other was using the PCA feature fusion algorithm. And from those new features from the PCA, we selected some of them for the new data set. And the classification algorithms were the random forest, the support vector machine, the naive Bayes, and the multilayer perceptron. The accuracy scores, it basically tells from all the participants the amount of them that were correctly classified. So for each of the algorithms and for each of the data sets, for example, for the random forest and the original data set, of all the hyperparameter combinations that were tested, the best accuracy was 0.75, which means that 75% of the participants were correctly classified. However, since this was a cross-validation, this is actually a mean of the 10 folds of the cross-validation with the standard deviation. And the values in bold, they are the combinations that had the best accuracy for each of the algorithms. So for example, for the random forest, the original dataset had the best accuracy, and for the other three algorithms, the ReliefF had the best accuracy. So in the plot of the accuracy, we can see that the naive Bayes with the original and the PCA dataset had the worst accuracy overall, was reasonably lower than other combinations. The sensitivity is the amount of experts that were correctly classified by the algorithm. So we can see that it was high overall, except for the two naive Bayes combination here. And the specificity is for the amount of novices that were correctly classified, and we can see that it was a lot lower than the sensitivity. Let me go back to the sensitivity. And this is probably because the dataset was unbalanced, so it is likely that since there were less novices participants, the algorithm had then trouble identifying the novices participants during the classification, even though we use balancing algorithms. And finally, for each of the algorithm and dataset, we have a box plot of the accuracy across the cross-validation fold. So what this means is, for example, for the naive Bayes with the original dataset and the multilayer perceptron and the ReliefF dataset, we had that the accuracy across the cross-validation folds varied a lot, while in the support vector machine with the original and the PCA dataset, the accuracy across the cross-validation folds didn't vary much, which could mean that if we have some new data that is similar to the data they were trained with, these two would likely have a more consistent results during classification. So in conclusion, as I said, the imbalance of the dataset heavily affected the results, which was seen in the specificity metric. And this means that for this case, the accuracy metric cannot be the only metric that is looked at. The naive Bayes had the worst accuracy in most cases. The exception was for the ReliefF dataset, and the ReliefF dataset resulted in the best accuracy most of the time, and the exception was the random forest classifier. And thank you for your attention.
Perfect. Thanks a lot. It's a very interesting project. Yeah, really, really interesting. Let me see. Okay. I'm just curious because you mentioned about relief but SVM, vector machine. You mentioned it's more stable. Why do you think it happened? SVM is more stable.
Oh, you mean why I think that happened? I couldn't really tell why that happened. I thought that was more stable in the plots that I showed, because between the cross-validation folds, it had less variation in the accuracy. But why that happened? Yeah, I can't really tell you why.
No, okay. Yeah, I think it was interesting. The others really changed a
Yeah, yeah.
lot. Yeah.
Yeah.
And you mentioned a test with 155 dentists. They are all from the University of São Paulo, or did you get people from other places?
Yeah, they were. It was before pandemic, so it was two experiments. Both of them were in University of São Paulo. One of them was in Bauru, and the other was in São Paulo, the main campus. But
Okay.
yeah, they were all from USP.
And you took all the setup and moved there.
Yeah, that
Yeah.
took a lot of work.
No, yeah, but no, these haptics are not so. They're used. There are some very big and complicated ones, but this is a little bit more. Uh, Another point I was curious because you have like an accuracy 0.75, 0.80 something, I guess. Uh, do you think you can improve this in the near future?
So yeah, I have done some tests. I've used genetic algorithms for feature selection, which is a wrapper feature selection, and it did help. It did improve the accuracy, like by I think the in this paper the best I had was about 75 and got to 81. But yeah, I couldn't get any higher than that yet. Maybe with something else, but right now I couldn't get any higher than 81.
Okay. Are you doing a master degree? No? PhD?
Yeah, it's a master.
A master?
Yeah, I'm finishing my master degree.
Okay. Maybe in the PhD you
Maybe.
okay. I Yeah, no. Let me see. Just someone is no. Okay. I'm also curious because there is a visual feedback in the system, and I have a cat. Yeah, and yeah, the system I know for a long time this simulation system. Do you think that this visual and web ways can? I don't know how does it interfere in the results. I don't know if you have more realistic images or I don't know or more better feedback or worse feedback. I don't know. Do you think this can interfere a lot or not?
You mean the haptic feedback we have,
Yeah, or the
or
visual as well, because you see the images. Maybe you should have a better image. It can change the all the system. I don't know.
um, yeah, if you had a better image, you mean?
Yeah, for instance, or does it? It doesn't. It shouldn't impact the results.
I think it could. I know there are some issues on virtual reality itself about like sometimes image can get blurry depending on the distance and the resolution, of course, of the image. And in this case, it's a very specific, like there's a lot of precision involved, and it's inside the mouth of a child. So yeah, I think have if we had a better resolution, not just resolution, I think that's actually a hardware problem with virtual reality head mounted displays. But yeah, I think this could maybe change a bit on the precision of the user when they're trying to do the anesthesia, because it's not it's like the trajectory itself is very simple, but the procedure is not that easy to do because it's on the back of the mouth, and it's not that easy to have the best view, the best angle to do. So yeah, I think having better feedback, better visual, it can't hurt, right?
Okay. No, no, yeah, because maybe you have to look the other or other points. I don't know. You did a nice job, but maybe there is other things impacting, and
Yeah,
you should take a look.
yeah, definitely.
Okay. Well, I think we are on time. Someone with an interesting question? No, just Fatima, but doesn't work for you. Okay. Well, thank you. Thanks a lot
Thank you.
for your time, for your presentation, answering all my questions.
Thank you. It was my pleasure.
Okay. Let's go to the third paper. OAK-D as a platform for human movement analysis, a case study by Daniel Perazzo, Natália Souza Soares, Vitor Gouveia de Menezes Lira, Gustavo Camargo Rocha Lima, Alana Elza Fontes da Gama, João Marcelo Xavier, Natália Teixeira e Verônica Taischreiber. O Daniel vai fazer daqui a pouco. Sorry, Daniel is going to answer all the questions in a moment. Let's see the video.
Hello everyone, my name is Daniel Perazzo and I will present the work OAK-D as a platform for human movement analysis, a case study. This work was done at the Universidade Federal de Pernambuco and Voxel Labs. Firstly, what is the context and motivation for this work? Computer vision is everywhere. As advances in computer vision keep happening, have seen the development of many real-world applications, such as object and face recognition, scene segmentation, human and object tracking, and many more. For these kinds of applications, one current challenge is to make embedded AI, that is AI that is processed inside embedded systems, such as a Raspberry Pi. Lately, we have seen the development of highly specialized embedded systems for these kinds of tasks, such as the Jetson Nano. We chose for solution the OpenCV AI Kit with Depth, OAK-D, that features a high-resolution camera, significant compute power, and a chip that can run deep learning models. Moreover, it is also tiny, the size of a Raspberry Pi. Now, let's present the related works. Regarding pose estimation, one of the most well-known AI models is the OpenPose. This system enables 2D pose estimation of the human body, returning information about each limb, head, and chest. Many authors use this information to perform human movement analysis. For instance, Gama and colleagues use such a system in the context of rehabilitation and physiotherapy. This work computes the angles between the bones to make comparisons between the ground truth pose and the current arc, so that it can detect movements. In the context of sports, this type of information can be used in a football match, for example, as done by Stein and colleagues, by identifying weaknesses, performance, and potential improvements for better strategies. Other applications use the Microsoft Kinect camera for biomechanics analysis for single-player exercises in the same sports-oriented vein. After the release of the OAK-D, we noticed that this device has the potential to be a real game-changing platform for embedded AI applied to many fields. To test our hypothesis and be inspired by how exercises at home became very popular during the COVID-19 pandemic, we decided to develop a case study using the OAK-D as a platform for human movement analysis. We built a solution to analyze people's at-home workouts called Motion Analysis for Home Gym System, MAGS, for our case study. We use the OAK-G for the OpenPose inference. Since our model of OAK-G does not have a Bluetooth or Wi-Fi module, we use the PC or Raspberry Pi to compute a skeleton and send data to a smartphone via Wi-Fi. Finally, the smartphone, via a Unity app, calculates the body angles of the structure and returns this feedback to the user. So, the OpenVINO integration with the OAK-G enabled us to infer joint heat maps and recover the depth range of the scene. This data will further be computed in a 3D skeleton via PC or Raspberry Pi. A significant challenge for this application was the near real-time feedback. To improve our FPS, we decreased the image resolution and improved from 6 to 50 on the PC, from 3 to 7 FPS in the Raspberry Pi 4, and achieved 3 FPS in a Raspberry Pi 3. To perform our motion analysis, we used the iCap software, developed by Gamma and colleagues. This software is a motion analysis framework that, given the skeletal representation of the user, enables him to analyze his movement. This framework was developed in-house using Unity. With this information, we give feedback to the user regarding his movement. This type of feedback will enable the user to correct his pose. We also count the number of repetitions and create a mirror image of the skeleton of the user. And with this, we created our at-home workout system. We tested our system with two popular movements, the side lateral raise and the squat. The hypotheses we tried were: is the OAK-G able to detect the 3D human pose? Is the motion analysis system able to see and propose corrections to wrong movements? Is the motion analysis system able to correctly count repetitions? Validated our hypothesis with a series of tests and performed many exercises with our current solution. As we can see, have the skeleton imitator user, the open pose annotations, the feedback providing the type of exercise, the number of repetitions, and the message of correction when the user is executing the movement poorly. Now we reach our final conclusions. The OAK-G is suitable for many computer vision applications, has enough computational power, is portable, and is relatively low cost compared with other solutions. A case study highlights that the OAK-G could be used as an aid for home workouts. We plan on further developing this technology. For example, we are improving our system to allow movements and test our system as input for virtual reality scenarios. System won third place in the first OpenCV AI competition, sponsored by Intel. Thank you all for the attention.
Perfect. Thanks a lot. It was very good, very good.
Thank you.
Okay, let me see just if there's someone. No. Okay. Daniel, you mentioned a couple of times low cost. How much are you talking about your system? Just to give an idea.
Yeah. The OAK-G, the last time I checked, it was sold at a price tag of, I think, $150. Yes, $199. Yeah, for the camera and the AI processor. But it's like a big image quality camera. So like it's cheaper than buying a AI processor and a high-end camera.
I see. Okay. Yeah. Okay. It's appears to be a good price. And okay, but about your work, I just get a little confused in your presentation because you mentioned about frame per second, FPS, a top 7 frames per second, but in the movie, in the video, I saw like reaching 15. What's the maximum frame rate?
Yeah, in the video, but like I think you saw like it was I think was it was in the beginning of the slide. It was with just checking the open pose, and it was in a computer, if I'm not
Okay.
mistaken. And in the computer, the frame rate is much higher. But
Sure.
if we use a Raspberry Pi, it drops significantly.
Okay, to around the 7 frames per second.
Yeah, around this rate.
Okay, still, okay, it's not super good, but there is room for improvements.
Yes,
Good.
there's room.
Okay, and you did everything in 2D. All the tracking is 2D, not 3D.
And the OG has a depth sensor, so we use the depth sensor of the OG, also the all movements, which is registered then in 3D.
Okay. Then the track, the joint positions are in 3D.
Yeah, the joint positions are in 3D.
Okay. Then I misunderstood part. Okay. Let's see. Okay. And another thing, I believe because the COVID, you haven't room for many people trying your system. I see there are a few people. But did you get some results from people? How the feedback? Is the feedback good? People enjoy the feedback, or it's a kind of weird? How was the people response to that?
Yeah, we only run tests with one of the autos and other auto. So like there's like this room for improvement. Like we do more tests,
Okay.
but the people that use the app liked it, but it's in some areas it misunderstood some movements, especially movements that are in 3D, and there's like accuracy issues, but those are areas that we could refine.
Okay. Yeah, I think let me check it. I do have your paper here, but
Yeah,
I think it's missing some of these more like people using your system and the
yeah,
comparison, like with Kinect, for instance, like how Kinect is better to your
yeah,
system. Of course,
comparisons.
yeah, of course, might not be fair this comparison, but I think you should compare somehow and put some data in your paper. Okay, I'm trying to give advice. I don't know. Okay. I think for me, that's all. People are not interacting a lot with us. No questions. I can't see any question come up. Let me see here in the private. João Marcelo said you did the comparison in another paper, but does not accept.
Yeah.
Okay. No problem. But Daniel, thanks a lot.
Thank
And
you very
congratulations.
much. Thank you.
You're welcome. Okay. Let's go to the fourth paper, classification of human movements with motion capture data in a motor rehabilitation context, by Guilherme Luiz Silva Rodrigues, Diego Dias, Marcelo de Paiva Guimarães, Alexandre Fonseca Brandão, Leonardo Rocha, Rogério Iop e José Remo Ferreira Brega. Okay. After that, Luiz Guilherme will answer some of the questions. Let's see the video.
Hello,
I'm Luis Rodriguez, and this is the presentation of the paper Classification of Human Movements with Motion Capture Data in a Motor Rehabilitation Context. Our group is formed by students and professors from São Paulo State University, Federal University of São João del Rei, Federal University of São Paulo, and University of Campinas. This research was partially sponsored by Huawei Technologies. There are many studies that contribute with new technologies and applications that can help the area of rehabilitation by increasing the motivation of the patient, so it could have less chance of giving up the treatment. To make this technology more accessible to clinics and patients, we aim to reduce its cost. And we also want the system to understand more about the complex movements. Today, the body data are used to control the application in augmented reality and virtual reality, and this new implementation that we will present also stores the data and uses it to train machine learning models. In order to reduce the cost of the equipment, we built an application that runs on a device that most people already have, a smartphone. And we also developed a system that analyzes the captured data to bring insights to physiotherapists. The patient, in front of the camera, is asked to perform a movement, and the data are analyzed by the system. The required equipment for the system to run is the smartphone, and a bigger display is also recommended since the user needs to move away from the device to keep the body in the camera frame. We can also use a laptop or desktop computer with a webcam instead of the smartphone. In order to obtain the body information with only the image of the camera, we have used an existing framework called MediaPipe, since it's working on Android, iOS, and Windows. But there are other frameworks that can execute this task. This is the output of the pose tracking algorithm. Now we want to use the generated data in the machine learning model. The chosen analysis to be the proof of concept of the pipeline is related to the shoulder joints. So firstly, we select the joints related to the right side of the body and calculate the angles related to the articulation of the shoulder. You might be wondering why we calculate the angles. One of the reasons is that the original body tracking data is given in pixels, so the camera resolution will influence the results. Also, if the user is far from the camera, the pixels values would be smaller, and if the person is too close to the camera, the pixels values would be greater, even if the pose and the movements are the same in both cases. The same problem happens if the movements of the same type are performed in the left side of the camera or in the right. In image pixels, they are different, while in angles, they are consistent. Since we are working with movements that last from 3 to 15 seconds, we needed to collect the same feature at a certain frequency. For example, the right position has both arms pointed to the ground, and the value at that time is 0. When it goes to the purple and blue position, one of the arms is pointing to the side and then up, and its values increase. We have 3 variables because the selected set of joints can generate 3 different angles, according to the figure at the top corner. These angles are captured 30 frames per second, and the total frames depends of the duration of the movement that is performed by the user. The 3 types of angles are concatenated and reduced to an array of fixed lengths for all samples. And the exactly 270 angles are fed into the machine learning model. The first experiment classified 4 types of movements and the second 8 types of movements. It was defined the category of the movements related to the right arm to be recognizable and trainable. For training, we have created a dataset with about 300 recordings that contains different authors and devices, with a movement being performed and its real name attached to it to use it as the label for training the machine learning model. Most of the classes had very high accuracy, and the class with lowest precision was related to the elbow class. The presented pipelining of tracking, storing, and analyzing allow us to conclude that the smartphone, which is a recent solution for tracking the human body, has an acceptable precision for this context, similar to special depth cameras. A second phone or used as a remote control to set the movement's name. It's not necessary in the inference scenario because it's going to predict the name of the movement automatically. The good results of the model and the pre-processing techniques can be used as a background for more implementations, including a full-body dataset with more types of movements, different machine learning and deep learning models, other approaches like supervised learning, and I study in a rehabilitation environment. Thank you.
Good. Thanks for the presentation. The videos super interesting. And okay, Simon, I have a question from the audience. Oh, there he is. How do you deal with the lack of real 3D information from media pipes since the depth values are estimated relatively to the center joint?
Hello everyone, thanks for the question, João. And we have a depth value related to this hip center joint, but of course it's an estimation. But it's enough to triangulate an angle. So the depth is related to the shoulder and the elbow already gives us an angle. Did I answer the question? Okay.
I don't know. Let me see, because John did come up with other questions. Did you compare your solution? I think you can see in the comment. Did you? Yeah. Did you? Well, even better. Did you compare your solution with others that do not use machine learning? There are works since 2013 published in SVR that are quite precise for comparing body joints and they're far less complex.
No, I didn't see any reference of SVR. It's about comparing movements of the human body.
Yeah, this is the part that's complicated because the feedback's not.
Yes, that's the complicated.
Yeah, but well, SVR, there are many works in this. I don't know what the smartphone is for full body, but maybe I don't know. But of course, machine learning, as we see, well, this session for machine learning basically, and it's coming up in the last 2 or 3 years that are really huge amount. And in the past, there are other more standard solution, I guess, and would be interesting, I guess, if you compare how this evolved, how is it better, faster, cheaper, whatever from the previous strategies. I think that's the point.
And there are 2 parts of the paper. One is capturing. So we have used a deep learning CNN that is that is media pipe. Some of us here in events I already mentioned it. And the other part is the classification of the movements, right? So the classification part, this machine learning that I have used, I have used artificial neural network and SVM. The intention of this is to create a bigger data set and more complex movements. So it's a simple it's a simple task to do to classify a movement, but it can perform with more movements in the future. We can create movements for both arms at the same time and include lower limbs. That's why we are thinking about using machine learning.
Okay, I get you. You're more focused in this second part.
Yes.
Okay. Yeah, I understand. There's a lot of issues in complexity, and yeah, I'm mixing all this.
With machine learning, even unsupervised learning, someday we can use this data that was generated with motion capture, and then we can with patients in clinics, in rehabilitation clinics, we can use this data to cluster some patients with a similar pattern. So that's why we are thinking about machine learning with motion capture data. It can be from MediaPipe or it can be from Kinect.
Yeah. That I understand. You have this your solution simpler using just one camera. We can use more sophisticated cameras with 3D depth sensors, and the machine learning can improve the detection and understanding. Okay, perfect. I have just one last question. Actually, we discussed yesterday about the ethics. If there is a committee, did you pass your projects to a committee, ethical committee, or
it was used only with among the authors.
okay?
It didn't go to rehabilitation clinics yet.
Okay, but this is something you probably should look soon. I think
Yes.
yeah, I think even in our
have
conference,
a partnership with the brain, the CPD brain from Unicamp. So we are already thinking about this ethics committee.
Yeah. I think at conference we are going to work more on that. Perfect. Oh, our time's up, I guess. Thanks a lot for all the authors, actually. Super good. Thanks a lot. Opportunity for sharing a little bit of your knowledge with us. Okay, we are in this was actually the last presentation. Right now, we are going to have a closing ceremony in a few instants. And I think everybody here is invited to attend and see see what happened in this conference, what is going the future of the conference. Okay, then everybody is invited just in a few instants. Okay, thanks again, and I see you there. Bye bye.